Before diving deep into AWS networking, it is important to understand fundamentals of IP networking in general. So in this video, I'm going to give you a brief overview of important concepts of IP networking. It's not going to be very deep, it's more of a refresher. If you're interested to learn more, there are plenty of resources out there that will teach you this concept in much more details. Alright, let's get started. Okay, so in this example, I have client C with an IP address 10.1.100 and it wants to communicate with HTTP server with an IP address 10.1.20.100. And since this is HTTP, we want to send packets on port 80. Right, so let's first understand what is an IP address. So an IP address is a 32-bit unique identifier on an IP network. Now it can be represented as binary form. We also came up with human-friendly notation, which is this dotted decimal form. So let's take a look into that a little bit more. So in this case, we can split 32-bit address into groups of 8 bits. They're also called octets. So we split 32-bit number into 4 octets of 8 bits. And then what we can do is we can convert every octet into decimal form and put a dot. 10 in decimal can be represented as 0000. 1010 in binary. We can consequently do it for the rest of octets. This number at the top is a binary number. It's representation of this IP address. Common thing that you will see in IP networks is this NAT mask represented in slash notation. So NAT mask is a number from 0 to 32, which can also be represented as 32-bit binary number with a number of leading ones and then ending with the number of zeros. So this number from 0 to 32 represents how many leading ones there should be in the binary number. In this case, there is /24, so this means 24 leading ones. 3 octets out of 4, and then the last octet is all zeros. So there is another concept called network address. So this is how different hosts on an IP network can understand if they are on the same network or not. In order to get network address, we need to apply logical AND operation. If we do this, we will receive this number. We can also now convert it back to dotted decimal format, and this is what we'll receive. If we AND 10.1.100 with net mask 255.255.255.0, we will end up with a network address 10.1.1.0. If we take another IP address, so in this case of a destination, which is 10.1.20.100, ended with the same mask, we can calculate a new network address. So in this case, it's 10.1.20.0, and we can compare those two. So in this case, 10.1.1.0 and 10.1.20.0 are actually different network addresses. So that's how client C actually knows that HTTP server S is not on the same network as a client. Why is it important? Let's jump into the next diagram. Usually between two hosts, there is a bunch of networking infrastructure. So there are switches, there are routers, there are firewalls. They all perform different functions. So for this example, I'm going to focus only on routers. Client C is connected to router 1, server S is connected to router 2, so they are directly connected. They are also connected through this PR router as well. In order for client or pretty much any IP host to make a decision of where to send a packet, we consult what is called routing table. And the routing table exists even on the client. So in this case, on the client C, it will have an entry for its directly connected network 10.1.1.0/24, which is on the interface EN0, and it will have default route 000/0 going to 10.1.1.1, which is an IP address of router 1 over here. How does it know which entry to use? So this is where longest prefix match come into play. So if you want to send a packet to, let's say, 10.1.100 or 10.1.1.200, which would be on the same network as client C, it knows that it is on this interface EN0. It can look up and see that the best match, the longest match in the routing table is this one. So it will use this entry. It's important to understand that even 000/0 also covers that IP address, but because this one has longest prefix match, longest mask here, and it covers that IP address, that's why that is being selected. So if you want to send packets to 10.1.1, 200, it will use the second entry, even though the first one also matches. If you have the destination of the interface, it will use a protocol called ARP or Address Resolution Protocol, get some additional information. We'll cover that in just a second. In this case, we want to send traffic to 10, 100, 20, 100, so it will actually match only this entry because the second entry doesn't match at all. And in order to do this efficiently, there are some data structures. For example, there is tree data structure, which is Patricia tree, which allows to do this lookup efficiently. We know that we will send packet to R1. So what will happen on router 1? How does it know where to send it next? So when router 1 will receive this packet, it has its own routing table. If you don't do anything, it will only have entries for directly connected networks. In this case, 10.1.1.0, 10.12.0.0/30, 10.12.0.4/30, and their respective interfaces. Now, every router will need to know about both source and destination network, because very often we send packets in one direction, request for example, and then we send a response back. So we need to understand where to send that response packet. So that's why routers will need to know about both source and destination. So in this case, it actually knows about the source network via this entry, but it actually doesn't have an entry for our server. So where do we send this packet? We can see here on the diagram, we can send it here, we can send it here. Where should we send it? So that's where routing protocols come into play. And there are two main methods. So one of them is called static routing, which means that we will go to every router along the way and we'll statically configure all these routing details. So for example, I can go here to router 1 and say, well, if I want to get to network 10.1.20/24, I need to send it to my neighboring router, which is 10.12.0.2. Then I will have to do very similar thing on router 2 and on BR, pretty much on every router. So as you can imagine, it's not very scalable. It involves a bunch of manual configuration. There is another problem. What happens if this link goes down? How do we reroute traffic? So then we will have to reconfigure the static routes or use some other techniques. So that's not very scalable. In order to solve this, there is dynamic routing, and there are a bunch of different protocols. One of the most well-known is called OSPF, which uses Dijkstra shortest path tree algorithm in order to find the best way towards a destination. So the main function of a router is actually find the best path towards destination. Using a routing protocol like OSPF, routers can exchange information about the networks they know with each other, and this way they can figure out what is the best way towards destination. There are other routing protocols like RIP, EIGRP, and even BGP. After we do this, router 2, for example, knows about 10.1.20.0/24, it's directly connected network, and then using static routing or dynamic routing, it will know about the source network, which will be via 10.12, let's say 0.1, which is its neighboring router. So every router along the way will know how to send this packet. So let's trace it again. So client with an IP address 10.1.1.100 wants to send packet to 10.1.20.100. On every hop, we will consult a routing table. Our destination is here. So this is longest prefix match entry. So we'll send it to 10.1.1.1, which is here. Then this router will look up IP address of the destination again, which is 10.1.20.100. The longest prefix match for this entry is this, so we'll send it to R2, so we'll send it here, and then router 2 knows about that network as directly connected. It can send this packet directly to server. GP server on the right will send 10.1.1.100 as a destination IP address. It has its own default gateway, so it will send this packet to router 2. On the router 2 will look up this destination IP in this routing table. We'll find the longest prefix match here, so it will send it to 10.12.0.1, which is this one, and then router 1 knows about that IP address here as a directly connected network, so it will be like this. Okay. Cool. So now that we covered the basics of routing, let's look at the packet. Let's say we want to send an HTTP packet and it is post. Don't forget to subscribe. The client will create this HTTP packet. We have a body here which has action subscribe. We set an HTTP header which has post to /channel. Then we need to encapsulate this packet. So there is this TCP IP model where there are different layers which provide different capabilities. So there is application layer. This in this case will be HTTP packet. We will add an additional TCP header on top of it. The idea behind TCP protocol is that it will make sure that we have reliable communication between hosts. So in this case, we know the destination port number, which is 80 for HTTP. The source port, the client will choose at random. In this case, let's say it's this one, 45324. TCP is considered to be layer 4 protocol. On the layer 3, we have an IP protocol or internet protocol, which runs pretty much everywhere. The main identifiers on the IP layer are an IP addresses, which in this case we already know. So we have source and IP address, but then we come here to this layer 2 header, which is Ethernet. And the identifiers on the Ethernet layer are actually MAC addresses. But here is where we have a problem. Client will know its own MAC address. It's assigned to a network interface of every device by the vendor. When we create this packet, we need to provide a destination MAC address of the next hop. So you can see that in IP header, we have actually an IP address of the destination, but in the destination MAC address on layer 2 is actually MAC address of R1. So it's MAC address of this gigabit 0 interface of router 1. But how do we know this? There is this protocol called ARP, or Address Resolution Protocol. When we are on the same network, an IP address of this next hop is this one, 10.1.1.1, and our source is this one. We know that we are on the same network because we did our binary math. We can use this protocol in order to understand what is the MAC address of the destination, and it's pretty simple. We will send a broadcast frame to all hosts on the same network saying who is 10.1.1.1, and then router 1 will see this ARP packet and say this is my IP address. So then it will respond back with ARP reply indicating its MAC address. So by using this ARP protocol, every device on the same network can understand what its layer 2 address. So that's how this MAC address is populated. So we send this full packet here to router 1. So what does it do? We know that we need to send it to R2. What routers do is MAC rewrite. So they will change this source MAC address to router 1 gigabit 1 interface because it's over here, and then according to its routing table we need to send it to 10.12.02. We'll look up its MAC address using our protocol and we'll put it in the packet. So it will be MAC R2 gigabit 1. And hop by hop, every router will keep replacing this layer 2 information. But it's important to understand that from layer 3 and higher from this IP header, this full packet is intact. So only this layer 2 information is changed on hop by hop basis. Okay, so then this packet arrives here, and then what will happen is we'll change TCP header, we will reverse this information. So whatever the port was there, we'll reverse the IP addresses, and we will put our source MAC, and we will put as destination MAC address of the gigabit 0 of router 2. And then we again repeat the process step by step. Let's discuss the differences between two transport layer protocols, TCP and UDP. UDP is very simple and lightweight protocol. It doesn't establish connection. It barely has any features. There is no guaranteed delivery of the packets. There is no congestion control, no sending rate adjustment. And because of the lack of the features, the header is also very simple. It's only 4 bytes long. It contains only source and destination port, lengths of the data, and the checksum. In comparison, TCP is much more advanced protocol. It establishes connection, it provides features like reliable communication, it has built-in flow control, congestion avoidance. It's also considered to be fair. If there are multiple TCP connections going through the link, it will give equal opportunity to different connections to get a portion of it. In comparison, UDP just sends packets. It really doesn't care about anyone else. UDP is one of the most selfish protocols out there. Now, all of these features are actually very complex to implement, and it led to a lot of different optimizations and many different implementations as well. And from my perspective, TCP is one of the most complex networking protocols out there. It's definitely top 1 in my list, with top 2 being BGP. And it takes a lot of time and effort to understand it. I also think it's very important to understand it at least on some basic level, regardless if you're a network engineer or an application developer, mainly because TCP is the most widely used protocol out there. Now, if you want to learn more, check out Greer's content on YouTube. He has tons of great content about TCP. Alright, let's try to deconstruct this beast called TCP. So let's say we have a client and a server, and here you can see an exchange of packets over time. Let's start with TCP three-way handshake. When one side wants to communicate with another side via TCP, it sends the first TCP packet with SYN flag set. SYN packet contains a lot of negotiated parameters, so things like window and window scale, TCP maximum segment size or MSS, supported options, etc. So you should think about SYN packet not only as a first packet to initiate a connection, but also as a way to declare what kind of capabilities are there on one side. When another side sees this packet, it will send its own SYN packet in response, containing its own capabilities, but besides setting SYN flag, it will also set ACK flag or acknowledgement. Both SYN and ACK are set in the flags field of TCP header. When the initiator receives the packet with both SYN and ACK flags set, it will send an empty packet with acknowledgement flag set. Those three packets conclude TCP connection initiation and are called TCP three-way handshake. Now we spent on this three-way handshake one round trip time. We don't necessarily count this ACK because right after the initiator sends this ACK, it can also start sending the data. In some implementations, we can even send data inside of this ACK message itself. It is important to think about TCP in terms of round trip times, because in TCP every so often we need to send acknowledgements back to another side to let them know that we received the data. Let's cover briefly MSS or maximum segment size. Typical Ethernet frame can carry 1500 bytes of payload. Now IP header takes 20 bytes and then TCP header usually takes also 20 bytes. So we have 1460 bytes left. This number indicates what is the maximum number of bytes we can send in a single packet. There could be some encapsulations along the way going on between two sides. There could be some VPN tunnel and things like this, which consume some bytes for additional headers. In those cases, the intermediary routers can actually look in the TCP SYN packet and adjust MSS value. So this MSS value is set in the SYN packet by both client and the server, but intermediary routers can adjust this value. And this often happens if there are things like VPN tunnels which require additional headers. So those routers can actually decrease this value even further. They can set it to, let's say, 440 or 420. Now for this example, we will imagine that every packet that we send is 1000 bytes just for simplicity. Okay, let's now try to understand sequence and acknowledgement numbers in TCP. Using those numbers, TCP can guarantee reliable delivery of the packets. So in our example, the client is sending a big file towards the server. We can think about it as a stream of bytes. So TCP sequence number is a sequence number of byte in a TCP stream. We will not reset it between different packets. We'll keep incrementing this. So in this case, if I'm sending a TCP packet and I start with sequence number 1 and it is of the length 1000, so I'm sending bytes from 1 to 1000, and then the next byte that I'm going to send will be 1001. Acknowledgement number is a sequence number that is expected of the next byte. So let's say we received 1000 bytes. Acknowledgement number will say the next byte that I expect from you should have a sequence number 1001. So this is where this acknowledgement number comes from. Let's talk here about congestion window. It's also abbreviated as CWND. For this toy example, we set it to 1 MSS value, to 1000 bytes. In reality, most of the clients right now set it to 10x MSS. So if your MSS is 1460, it will set it to around 15 kilobytes of data. What is congestion window? Congestion window is a number of outstanding bytes for which we didn't receive an acknowledgement yet. Those are bytes that can be in flight that are not yet acknowledged. So the bigger the window is, the more bytes we can send before we actually receive an acknowledgement. If the window is small, then we will not be able to send data very fast, because for every, let's say, 1000 bytes, we will be waiting for acknowledgement and we will not be able to proceed further. So congestion window is what actually allows us to adjust the sending rate to the available bandwidth of the link. For this toy example, I set it to 1 MSS value. TCP algorithm has two parts. The first one is called slow start. The second part is called congestion avoidance. Slow in slow start is actually misleading, because during slow start it will actually be exponential increase of the congestion window. The idea here is the following. If I send a packet with a sequence number 1000 byte of length, and they were successfully received here, and the acknowledgement was sent expecting the next byte, which is 1001. When I receive this acknowledgement, I can double my congestion window size. Our window size is now 2 MSS or 2000 bytes. We can send in rapid succession two packets, 1000 byte each, in total having 2000 bytes in flight without acknowledgement. Sequence number of the first one is 1001, sequence number of the second one is 2001. When the server receives those two packets, it will send an acknowledgement back with the sequence number of the next expected byte, which is 3001. Because the last byte which was received had the number 3000. When the client receives this acknowledgement, it can again increase its window size exponentially. From 2 MSS value, we now jump to 4, which is 4000 bytes. In this example, it also had slow start threshold set to the same value of 4000 bytes. In real systems, this slow start threshold is actually pretty high to allow rapid increase of the sending rate. As a result, TCP will now transition to the next phase, which is called congestion avoidance. It is also often referred as AIMD, additive increase multiplicative decrease, because we will now increase our window size linearly instead of exponentially, but we will now decrease it by a factor of 2. So now that window size is 4000 bytes, we can send 4 packets in rapid succession of size 1000 bytes each. So 4 packets with sequence number 3001, 4001, 5001, and 6001. 4000 bytes total in flight without acknowledgement yet. Once the server receives all of those packets, it will send the acknowledgement for the next expected byte, which is 7001. When the client receives this acknowledgement, it will increase its window size linearly instead of exponentially. So it will go to 5 MSS value instead of 8. So window size of 5000 bytes allow us to send 5 packets in rapid succession. Let's say again server receives all of them successfully, and it will send acknowledgement number for the next expected byte, which is 12001. Let's say our client receives this acknowledgement successfully. It will now again increase its window size linearly, so from 5 MSS to 6 MSS, which allows to send 6000 bytes without receiving an acknowledgement. So we send these 6 packets, one of them will experience loss. So this packet with sequence number 15001 will not actually get to the server. Let's take a step back and actually understand what is packet loss. Why does it happen? So it's actually pretty rare for loss to happen because of physical problem with the link. Most often than not, the packet loss occur because there is congestion somewhere. So there is some link somewhere where some router wants to send more packets that link allows. Those packets will be queued on the router. Because queues are not finite, the excess of packets will be dropped. So that's often the case. Okay, so what will happen if the server will not receive this packet with sequence number 15001, but it will receive the other two, 16,001 and 17,001. So in this case, server will send an acknowledgement for the next expected byte, which it didn't receive. The server didn't receive the byte 15,001. So this is the number which will be sent in acknowledgement. Hey, I am still expecting from you the packet 15,001. Because it will receive other packets, the server might also send this acknowledgement packet several times in a row. In this case, it will send 4 of them. So the original one and then 3 more duplicates. And one of TCP optimization is when 3 duplicate acknowledgements are received, the window size will be decreased by a factor of 2. So from 6 MSS to 3 MSS. So that's why it's multiplicative decrease. It will immediately retransmit lost packet as well as the ones after. So it will resend these packets 15,000, 16,000, 17,001. You might ask, why do we have to resend 16,001 and 17,001? That's yet another optimization that appeared later called selective acknowledgement. As part of the acknowledgement, one side of the TCP connection can inform that it actually received packets from 16,001 till 18,000. But in the original spec, that wasn't the case. So if a particular packet is lost, we have to retransmit not only lost packets, but packets after that as well, because TCP guarantees in-order delivery. Okay, so let's say in this case, all those 3 packets were successfully sent. The server sends an acknowledgement with the next expected byte, which is 18,001. And in this case, client doesn't have any more data, so it can send packet with fin flag set. The server can reply with acknowledgement and also fin if it wants to close connection as well. And then the client will have to finalize the connection with its own ACK. There are several variations of this connection termination. One situation when the connection can be half closed, so only one side closes the connection and then later another side will close it. Another variation is where both sides close it at the same time. That's TCP in a nutshell. There are many different implementations. Those are just a small fraction. The original was Tahoe. Reno was very popular for a really long time. There is Vegas, QUIC. I think QUIC right now is default on most of Linux operating systems. There are some other implementations as well. If I remember correctly, one of the optimizations in TCP Reno, for example, was when 3 duplicate acknowledgements are received, the window size is being halved, and then we immediately retransmit lost packet. There are many more other optimizations. There are things like sliding windows. There is adjustment for the expected bandwidth. That's what's happening in QUIC. There is adjustment for expected round trip time, which was done in Google implementation called BBR. There is many more things. Okay, so what's the takeaway here? Well, TCP is one of the most popular protocols out there. You need to know at least some fundamentals about it. If there are a lot of round trips and there is also high latency, this will decrease your maximum throughput. You have to wait for those acknowledgements, and the higher latencies, the longer we have to wait, which means the longer we cannot send more data. Another thing I wanted to mention is, even though UDP doesn't have any reliability mechanism built in, you can still build reliable protocol on top of UDP by implementing this on the application layer. Let's talk very briefly about TCP, TLS, and HTTP. So very similar picture, but now we actually want to send HTTP post, for example, from client to server, and we also want to use TLS. So how will that look like? First, we will establish our TCP three-way handshake, which will take 1 round trip time. We can discard this TCP ACK because right after we send it, we can immediately send the next packet. In TLS 1.2, we need to spend 2 round trips. There are 4 packets. So client hello, then server replies with its own certificate and server hello. Then there is key exchange and then change cipher spec packets. 4 packets in total, which means 3 round trip times. If you have high latency, it will take time. And only after this, we can send our HTTP data. There are a lot of resources wasted on this. So there were many attempts to reduce this number of round trip times and do something smarter. If possible, you want to avoid as many round trips as you can. So one of the optimizations was TLS 1.3, which changed this from 4-packet exchange to 2-packet exchange. We still needed to spend time on TCP three-way handshake though. I want to point out that you really need to think about your round trip times. So if you can use things like TLS 1.3, definitely do it. If you can bundle a bunch of operations in one, so let's say you are talking to some API or database, please don't send a bunch of individual requests. Bundle them together. If it's possible to put stuff in a single request, please do it, because otherwise you'll spend a lot of time on round trips. If you can reuse connection, also do it, because you'll spend more round trips unnecessarily. When your source and destination is very close to each other, so let's say on LAN or local area network, where your latency will be less than 1 millisecond, a lot of these issues can be masked. If between two hosts there is WAN or wide area network, the latency there can be unpredictable. Might be 5 millisecond, it might be 60 millisecond, it might be even higher. If you can put your source and destination very close to each other and there is a lot of exchange going on, you should probably do that. Anyway, let's go back to discussing HTTP. In HTTP 1.0, you couldn't really reuse TCP connection. So for every new request, you had to make a new TCP connection. So you want to get your JavaScript, create a new TCP connection. You want to get your CSS, create another TCP connection. Now at some point, what browsers started doing is actually do multiple TCP connections in parallel to the same destination. So you would open multiple connections and request data in parallel. Now, it's also important to understand that different connections will fight for resources between each other. Then in HTTP 1.1, there was this attempt to have persistent connection, but there wasn't really true multiplexing built in, so you couldn't prioritize some things over another. So if let's say you requested a big image and it takes a long time to load, while you could at the same time request process your GET, until that image will finish delivering, your short GET will not get processed. There was a lot of implementation problems with how this protocol should actually work. Those persistent connections didn't really solve anything, so people still were relying on creating multiple connections in parallel. And browsers allow to do that, though they limited, I think, up to 6 simultaneous connections or so. Then HTTP 2, also known as Speedy, came along, and it came back with a lot of different optimizations, data compression, reusing the same TCP connection, but allowing to multiplex data. So while you request an image, you can say, hey, can you also send me this JavaScript? And it's really important, can you get it to me right now? Because I need to render my page. So there were a lot of optimizations in HTTP 2.0, but it still suffered some problems caused by TCP and TLS. TCP is implemented in kernel, and even though you could do this multiplexing, if you experience some packet loss, the kernel would not give the stream to your application, causing head-of-line blocking. So if the packet was lost, you couldn't really start processing the next received bytes. The second big problem was related to TLS. There was head-of-line blocking also in TLS due to cipher block chaining or CBC mode being used, where in order to decrypt the next block, we actually needed previous block to be fully decrypted. And if you experience packet loss, you cannot actually do that. Another interesting thing is that since HTTP 2 uses a single TCP connection, TCP algorithm AIMD hurts it even more than if we were to use multiple TCP connections. So there was this new protocol QUIC invented to eliminate a lot of problems of TCP and TLS, especially regarding head-of-line blocking. QUIC uses UDP underneath, not TCP. Reliability is built into the protocol on the application layer itself. It combines a lot of ideas from HTTP 2, but is also free from problems created by TCP and TLS. It has also additional optimizations. It still tries to be fair, so a single stream doesn't consume all bandwidth of the link. At the same time, it has even more optimizations than TCP has. There are also interesting ideas like, if you already presented a certificate to me yesterday, why should I request the certificate again? And many other things. I would strongly encourage you to watch this reInvent talk, where the creator of QUIC protocol explains this in much more details. It's really fascinating talk. Let's go back to our packet exchange between client and server and zoom in on this segment between client and the router. Now here we have a bunch of clients and our router, and between those we have layer 2 infrastructure. One of the most common protocols used there is called Ethernet, though there are also other layer 2 protocols, for example Wi-Fi, but here we'll focus only on the Ethernet. On layer 2 we also have possibility to segment traffic into different broadcast domains using technology called VLAN, and the standard for it is called .1q, and the idea behind that is clients from one VLAN cannot send frames to clients in another VLAN. If any client would send a broadcast message, only other clients in the same VLAN would receive this broadcast message and clients in other VLANs would not. In this case I have client B, D and E in VLAN 20 and client A and client C are in VLAN 10. So if client C were to send a broadcast frame, it would reach clients D and it would reach client E, but it would not reach client A and C. So on switch, generally you have two types of interfaces, access or trunk. Ports towards client will be in access VLAN. So in this case, we would configure here access VLAN 20, and between switch 1 and switch 2, we would put trunk, or maybe between switch and router, we will also put a trunk. If client B will send any frame, let's say broadcast frame, it will not have this number 20. When switch 1 will send this frame towards switch 2, it will add this additional header. It's called VLAN header or .1q header with VLAN 20 in it. So when switch 2 receives it, it actually knows that frame belongs to VLAN 20. So it can send it only to clients in the same VLAN. So in this case, it would be client E and also to router 1 if it's a broadcast frame. We already discussed ARP protocol, and when we send a broadcast frame, we put as a destination MAC address all Fs. By the way, MAC is a 48-bit number and it's often represented as 3 groups of 4 hexadecimal numbers. So let's say client B sends an ARP request asking for an IP address of client E. So destination MAC will be all Fs, and in this case, MAC address of client V will be all Bs. What will switch 1 do with it? So the usual behavior of a switch when it sees a broadcast frame is to flood it on all interfaces in the same VLAN or trunk, allowing that VLAN as well. So in this case, it will be sent to switch 1 and it will be sent to 2 trunks. And then switch 2 will flood it also to all ports in the same VLAN, like this. What about link between switch 2 and switch 3? What would happen if switch 2 would also flood this frame to switch 3 over trunk and switch 3 would also flood this frame to switch 2? Well, those switches would again replicate this frame on all interfaces where that VLAN is allowed. So client E would receive this frame multiple times, but then switch 3 would also send it to switch 1. And you can see that then switches will keep replicating these frames, causing what is known as a broadcast storm. So why it doesn't happen? Well, that's where another protocol comes into play called spanning tree. And layer 2 switches will participate in spanning tree protocol when they boot up with the purpose of creating a spanning tree. Once this algorithm runs, one link in this triangle, for example, between switch 2 and switch 3 will be blocked, essentially breaking this loop. So this way, when client B sends a broadcast frame to switch 1 will send it to switch 2 will flood it to client E, to flood it to router 1, but it will not send it to switch 3 because that link is blocked. Switch 1 also will send it to switch 3, and then switch 3 will also flood it to client D. Spanning tree ensures that there are no loops, that broadcast storm cannot happen. There are multiple variations of this protocol. There is per VLAN spanning tree, there is rapid spanning tree, there is multiple spanning tree, but this is outside of the scope of this video. What else will happen on switch 1 when it receives the frame from client B with MAC address all Bs? Well, switches have MAC address table, which is created on per VLAN basis. So for example, there is MAC address table for VLAN 20. So the MAC address all Bs on the port gigabit 01. There is also a MAC address table for VLAN 20 on switch 2. So when the broadcast frame from client B will be received there, we will also write down on which port we saw this MAC address. So in this case, we saw it on the port gigabit 02. So then the client E will receive this broadcast frame and its ARP request for this IP address 10.1.20.30. So client E will respond with its own MAC address, in this case EEEE, destined to MAC address all Bs. And when this will happen, switch 2 will also write down its MAC address, in this case maybe it was here on the port gigabit 01, and it will look in the destination MAC address of that frame. It will be destined to all B's MAC, and it knows on which port that lives. So it will send it on gigabit 02 back to switch 1. And then switch 1 will also add all E's to its MAC address table on, let's say, port 02 here as well. It will look in the destination MAC address of this frame, which is destined for all B's MAC address. It has it in its MAC address table on the port gigabit 01. So then this frame will be sent back to client B. Very often between switch and router there is trunk, though it's not obligatory. And when that happens, usually on router we would configure sub-interfaces to allow to send frames tagged on the same link. Okay, I hope this gave you some perspective on how layer 2 forwarding works. Let's take a look at this picture where several clients are connected to switch and there is a router. The question is this: how does client know its own IP address? Very often on servers we configure IP addresses statically, but on clients very often we use some kind of automatic mechanism to get an IP address. And there is this protocol called Dynamic Host Configuration Protocol, or DHCP. And there is a special process called DORA for packets that allow us to configure an IP address on a client. So when the client machine boots up and it has DHCP configured, on that interface it will send a broadcast message that will reach every host on this network. So it will go like this, saying, hey, I would like to get an automatic IP address. Can I get an IP address? If there is a DHCP server, and in this case it's a separate device than R1, and it has actually DHCP configured, and it has this configuration with pool, with NAT mask, with default gateway, and a DNS IP address. DHCP server keeps track of all clients that requested its IP addresses, and it will get an available IP address from this pool range and will send this information back to the client in the offer message. So the first message was discover, hey, I need an IP address. DHCP server replies with offer. It will actually reply also broadcast, and then client will like, okay, great. It will send a DHCP request confirming that, hey, I would like to use this IP address that you offered. And then DHCP server can acknowledge it with acknowledgement message, and this finishes DHCP configuration, and client now knows its IP address, default gateway, and DNS IP address, or domain name server. So let's try to understand how DNS works. Okay, so in this next scenario, our client 10.1.100 wants to understand the IP address of AWS Amazon.com, which is over here. So we need to resolve AWS Amazon.com to this IP address 18.244. So how do we do that? We just learned that the client will have an IP address of DNS server from DHCP server or statically configured. So it knows the IP address of the DNS server. So there are different types of records in the DNS. DNS, it's at the database which has the mappings of domain names to IP addresses and vice versa, and some extra information. So one of the main records is a record which contains exactly that. So it will have an A entry for, let's say, AWS Amazon.com will be mapped to an IP address. Now, when the client wants to get an IP address, so it will send this DNS A record request to the DNS server. When this DNS server will receive this query, it will try to get it from authoritative source. So the first thing that this DNS server will do, it will reach out to the root name server. And there are 12 of them, and there are 12 well-known IP addresses. Those are usually in the software directly. In this case, there is this rootservers.net with this IP address. DNS server will know about this IP address already, because this is one of those 12 well-known IP addresses. So it will ask a root name server, hey, what is the authoritative name server for .com? And the root name server will reply with a domain name for .com name server. In this case, it's agtldservers.net, also called TLD name server, top level domain name server. It will reply with both domain record as well as IP address in the additional section. So this is what's called glue record, but let's not go into that details. It will reply with both agtldservers.net and IP address of that name server. So then DNS server will query TLD name server, hey, give me the authoritative name server for Amazon.com. And again, the TLD name server will reply with both domain name of the name server for Amazon.com, which is ns1 amazondns.com, as well as IP address in the additional section. And then lastly, DNS server will query that authoritative name server saying, hey, could you please give me a record for AWS-Amazon.com? And then the authoritative server will give you an IP address. Now, once we have this IP address over here, we will reply to original client with this IP address. So now the client using this process will know that AWS-Amazon.com has a mapping to this public IP address. Also here have Linux server, and using dig command you can look in these details. So if I dig with trace an additional option for the same thing, I will see a number of DNS queries. So in this case, this whole DNS resolution will be done by your own machine. We are having an entries for our root servers, then we will query for .com and we will get agtld, and then in the additional section we'll receive an IP addresses. And then lastly, we'll query for name servers for Amazon.com, which is this one. And in the additional section, we'll also have an IP address. By the way, with Quad A records, we have IPv6 addresses. And then lastly, we'll query Amazon.com name server to get an IP address for AWS Amazon.com. In this case, it replies with CNAME, which is can think of as like an alternative name. And if I, let's say, just do dig, at the very end, we will receive an IP address. Okay, cool. So this is DNS. DNS is actually quite a complex topic on its own, and it's really important you understand DNS regardless if you're on premises or on AWS, or even if you're an application developer, because there are many problems associated with DNS that can happen in your environment. All right, so let's cover the next part. As I already mentioned, two different hosts on IP network need to have different IP addresses. I also mentioned that an IP address is a 32-bit number, which means the maximum number of IP addresses is around 4 billion. It was very clear from the beginning that we will exhaust all available IP space. So there were several ideas in order how to slow down this IP exhaustion problem. One of them having some IP space reserved for special use. Another one is network address translation, or NAT, which allowed to convert many IP addresses into one. Now here I have only several of those reserved ranges, and those you will also see on AWS, so that's why I wanted to cover those. The most well-known IP range is RFC 1918. IP ranges reserved for private use. Those are 10.00/8, 117.16.00/12, and 192.168.00/16. Another range that was originally reserved for carrier-grade NAT, but it can also be used for some other purposes. It's also not routed on the internet. So this is 164.00/10. And lastly, there is link local IP range, which is 169.254.00/16, which should be only significant on a link. This range is also used by some services on AWS. inside of a VPC. Now, all of those IP ranges are not routed on the public internet. And especially those first three, those are very popular private IP ranges that are used within your own networks and within your own organization. It's very likely if you're watching this at home or at work, your computer or your phone has an IP address from one of these three ranges. Let's first understand how we can route on the internet with public IPs, and then we will take a look at network address translation. So first, how does the internet work? The routing protocol that is being used on the internet is called BGP, or Border Gateway Protocol. It's a highly scalable routing protocol, and it was invented because other routing protocols, which I already mentioned, that are mostly used internally within the organizations like OSPF, they couldn't work on internet scale. There are many routers on the internet which exchange public IP addresses, and unlike your own private organization, internet is always in flux. There are some links going down, there are some new prefixes being advertised from new places, and we need a routing protocol which could support this constant churn. And BGP does that, and the whole internet runs using this routing protocol. Now, because we are now talking about this huge internet scale with thousands and thousands of routers and public IP ranges. And on this scale, we needed to think about not only individual routers that our traffic passes through, but actually the whole organizations that the traffic goes through. That's where this term autonomous system was invented. I looked up definition of that and it didn't really help me explain this term better. You can think of autonomous system as of network boundary of an organization, which has its own set of IP prefixes and its own routing policy. Now, there is autonomous system number. This is an identifier of autonomous system of your organization on the public internet, which is assigned to you by a central entity. Let's say we have this company Acme, which has ASN 456 assigned to it. Now, within this organization, we use some private IP space, in this case 10.1.0.0/16, to assign IP addresses to all of IP hosts, to client, to servers, to routers, etc. Now, this organization also owns an IP space 209.165.200.0/24, which it advertises to neighboring service providers, ISP1 and ISP2. Those ISPs have their own AS numbers assigned to them, in this case 100, 200. There is also here an Amazon network, which for this example has ASN 7224. Now, Amazon owns many IP addresses, but for this example, let's say it owns an IP range 18.244.128.0/23. Inside of this range, we have an IP address for that HTTP server awsamazon.com, which we resolved using DNS before. Amazon will advertise its own range to its neighbors, to ISP1 router 5 and to ISP2 router 9. And then Acme organization, since it owns 209 range, it will also advertise this to router 5 and to router 9. BGP as a routing protocol has many different attributes that can influence what path we will select. After we advertised our BGP prefixes to neighbors, ISP1 and ISP2 will advertise these prefixes to their own peers and to each other in this case and to Amazon. And eventually these prefixes will propagate from Amazon to Acme and from Acme to Amazon. This is how it will look like. So there is BGP routing table. It has this prefix from Amazon and it can go via router 9 and go via this router, or it can go via this router. One additional attribute here will be AS pass. The idea behind AS pass is every time the BGP advertisement passes some autonomous system, it will add this number to the list. So in this case, this advertisement was originated from AS number 7224, then it went to router 9, which is AS 200, and then it arrived to company Acme. And then through router 5 have something similar, but then it originates from 7224 and then it goes through AS number 100. Amazon will see something similar in this case. This BGP advertisement was originated by ASN 756, and then from router 5 it will add AS number 100, and router 9 will add AS number 200. BGP uses what's called best path selection algorithm to compare different attributes in specific order and select the best path. And I will very briefly cover only two. So the first one is called local preference. Now local preference is almost at the top of the BGP best path selection algorithm, and it's a number where the higher number is better. And using this higher number, we can prefer one route over another. And usually we use local preference to select exit point for our own network. So from London Edge perspective, if on an incoming BGP advertisement, so on this BGP advertisement coming to London Edge, this London Edge router will set that local preference coming from router 5 is 200, and the local preference for a route coming from router 9 is 100, then 200 will win. So this way we can prefer router 5 as our exit point. Local preference is often used for outbound. Now, what if company Acme really wanted to make sure that inbound the traffic prefers coming via router 9? So that's where we can manipulate this AS path attribute, and in terms of AS path we compare the lengths, how many of ASs we traverse. And what London Edge can do when it does this BGP advertisement, if you want to make router 9 preferred as an inbound towards other routers, we can increase AS path lengths by putting our number several times. By default, we will add our ASN number only once, but we can actually add it multiple times, and this is called AS path prepending. Towards router 5, we can append our AS number 3 times, and towards router 9, we'll only do it once, like a normal way of operation. So this way, when Amazon will receive this prefix from router 5, it will have this longer AS path, and from router 9, it will have shorter AS path. Unless we change something else, it should prefer router 9 as an exit point. However, AS path is much lower in the algorithm than, let's say, local preference. So in this case, Amazon network could technically apply local preference to still prefer router 5 regardless of AS path length. Now there is this another technique called community string, some arbitrary number assigned to a BGP advertisement. And there are some well-known community strings, they're also custom one. And the idea is very similar how you use tags in other places. So for example, you can have a tag which has environment production or environment development. But in BGP, what you can say is, if you send to me a community string, let's say 1:1, I can predefine my own set of community values that means something to me, and then will do something on my network automatically. Now, many service providers have their own set of defined community strings, which means something to them. You as a service provider can say, if you send me this community value 1:1, my router will apply local preference 1000. And then if you send me another tag value, let's say 1:2, I will apply local preference 500. So this way you can send a tag to me to influence how I send traffic to you. So it's a very powerful technique. The reason I mention a little bit more of these details about BGP is because if you will want to connect to your on-premises network using technologies like AWS site-to-site VPN or Direct Connect, those will be the mechanisms that you can use to impact outbound and inbound traffic. As the end result of this BGP advertisement, London Edge will install a route towards 18.244.128.0/23 via, let's say, router 5. And then Amazon router will install route 209.165.200.0/24 in its routing table via some neighbor as well. Okay, great. Now the border router in Acme company will know about Amazon prefixes, and Amazon border routers will know about Acme company prefixes. That's great. Okay, but how do we actually route from our client, which has an IP address 10.1.100, to this Amazon web server, which appears on the internet with this public IP address? But actually it will have some other private IP address that we don't even know about. Let's say in this case 10.1.1.1. Okay, so we want to communicate from this client to this server. On the internet, we must communicate with public IP addresses. Both client and the server have private IP addresses. So what do? Now we actually want to connect to this public IP address. We will use a local routing table and default gateway to send this traffic to router 1. Now, using some mechanism, this border router London Edge can actually propagate this route from Amazon it learned through its own network. So router 1 will know that it needs to send it to London Edge. And then we discussed, let's say London Edge will want to use router 5 as next destination. Okay, but what do we do about this IP address? Because this IP address will appear as a source IP in the IP header. So that's where many-to-one NAT comes into play, and it's also known as PAT or port address translation. The idea behind PAT is that you can take many IP addresses and translate it into one. In this case, we'll translate all of our private IP range into the single public IP address 209.165.200.100. We'll also have to keep track of every flow so that for return packets, we can actually translate it back to our host. So in this case, let's say the source port that was selected by the client was port 45234. This border router will add source IP and source port, and it will translate it to this public IP that it owns and some other port that it has free. And what will happen is we'll actually change source IP address in the IP header of this packet. So now we have a public IP address, so we can actually send it to router 5, then router 5 can send it to this router, and then maybe it can even send to this another router. Okay, how do we translate this public IP address to this private IP address 10.1.1.1? Well, that's where another type of NAT comes into play, which is one-to-one NAT. And compared to the previous one, this one will be stateless. So in this case, we'll configure on any router that will translate 18.244.129.231 to an IP address 10.1.1.1. We don't have to keep track of connection because this is one-to-one. Whenever we see one IP address, we can convert it to another. We will change destination IP in the header to this private IP now, and then this packet will arrive on the server. Now the server can reply as a source IP address, it will be 10.1.1.1. As a destination IP address, it will be this IP address. When this packet arrives on this router over here, it will again look that it will have this one-to-one NAT translation, and it will convert it back to 18.244.129.231. So this packet can now traverse the internet. So it can go here. So this packet can go here. It can come back to this London Edge device. And in this London Edge device, we keep track of this connection. We know that there is some return traffic coming to this IP address in this port. We should translate it back to this IP and this port. So that's what that router will do. We will change the destination IP address now to private IP address, and now it can traverse our network. So things you need to remember is that one-to-one NAT is stateless, but PAT is stateful, and routers need to keep track of connections in order to do that. Now in my next video, you will see how these concepts directly translate to abstractions provided in the Amazon VPC. Now there is one other topic that I want to explain very briefly, and this is VPN or virtual private network. The idea behind VPN is to create an overlay network on top of some existing underlay network and extend it to remote network or host. Now VPN doesn't implicitly mean that must be encrypted, but using something like IPsec VPN, we can actually encrypt traffic on this overlay. There are two main types of encrypted VPN that are commonly used. One of them is called site-to-site VPN. The idea behind site-to-site VPN is to connect two remote networks to each other. And another common type of encrypted VPN is called remote access VPN. This type of VPN allows a particular host to connect to a network in secure manner. So for example, if you use something like Cisco AnyConnect or OpenVPN client, you can VPN into some remote network and appear like you are part of it. Okay, so very briefly, let me show to you how this could work. Now, let's say this company Acme actually has a remote location in Frankfurt. over here. The main office in London is connected to the internet, and that remote location also is connected to the internet. On top of insecure underlay internet infrastructure, establish a secure communication between London Edge and Frankfurt Edge. Then the tunnel can appear as yet another interface on a router. We can run some routing protocol on top of it. And then as a result, London Edge will learn about a route to the remote location, let's say this one. And then Frankfurt Edge router will learn about our head office IP space also via tunnel. Let's also take a look at the packet exchange for IPsec VPN. So in this case, I have router 1 and router 2. In order to establish site-to-site IPsec VPN, usually a protocol called IKE or Internet Key Exchange is used. And there are two versions of it, IKE v1 and IKE v2. In IKE v1, you will also sometimes hear the protocol called ISACAMP. And in IKE version 1, it's broken down into two phases, phase 1 and phase 2. Phase 1 can be done in main mode, which has 6 packets, and aggressive mode, which has 3 packets. And then in phase 2, there are 3 packet exchange, which are called QUIC mode. The idea of phase 1 is to establish a secure management channel first, and then on top of that management channel, we will establish phase 2 security association or SA, which would be tunnels allowing us to send encrypted data. Now for all of these 9 packets, they will be used source and destination port UDP 500. Packets 5 and 6 of main mode will already be encrypted, as well as all packets of QUIC mode. And after we are done with all of this, and after phase 2 SA came up, we can start encrypting our data, and we will encapsulate our packets into protocol called ESP. So this is not TCP or UDP. This is yet another protocol. If we have our data, so let's say our original packet is this. We have an IP header, TCP header, and then also TCP data. So it will be HTTP header, let's say, and HTTP data. We add an ESP header and an ESP trailer. We also have ESP authentication, and then we will add a new IP header where source IP will now be router 1 IP and destination will be router 2 IP. All of this will be encrypted, so we will actually not be able to see those IP addresses or the data at all. So this way we can securely send packets even via insecure communication channel like internet. Sometimes between router 1 and router 2 there is NAT or network address translation. This NAT can be identified using the feature called NAT traversal. Both sides need to support it. The fact that NAT is being used will be identified in packets 3 and 4. And what will happen from this MM5 packet is we will transition to using UDP 4500. We will use UDP 4500 not only for MM5 and MM6 messages, but also QUIC mode and even ESP encrypted packets. So we'll take ESP packet, we will add an additional UDP header, so ESP packets will be encapsulated. And this is done because NAT devices cannot work with ESP directly. This is actually quite important in the cloud. If you put a virtual router on AWS, public IPs are not assigned directly on the instances and there is NAT being used. So that communication will actually use UDP 500 and UDP 4500. When IPsec VPN without NAT in the middle will use UDP 500 for phase 1 and phase 2, but then there will be plain ESP used for the data. So remember that if NAT is used, then instead of UDP 500 plus ESP, you'll be using UDP 500 and UDP 4500. So you need to make sure that your firewall allows that traffic. There are many advancements in IKE v2. It's considered to be much more secure. And there is only 4 packet exchange to establish SAs. There are 2 messages called IKE SA init, request and response, and then there is IKE auth, request and response. After that, we can send our encrypted data. If possible, always use IKE v2. It's much more secure protocol with many advancements. Alright, that was VPN. Whew, that was quite a lot. I think I covered everything I wanted, but honestly, I don't know how I did. Was it too long and I bored you with so many details? Or maybe vice versa, you really wanted me to cover these topics in much more details than I did. Let me know what you think in the comments. Thank you, and until the next time.